name is Richard Berger. I work at Los Alamos National Lab. And together with my colleague Hyun Lim, we'll be talking about HARD. That's a multiphysics code that is implemented on top of the FleCSI framework. Yeah, with the name, the jokes write themselves. Everything's hard in this problem. Okay, so my part is giving you a high-level overview of what FleCSI is and so how we use Kokkos. Okay, all of you know that modern HPC systems are increasingly complex. So you have millions of cores, you have different accelerator types, you have heterogeneous systems. And now it becomes really hard to get good performance on these systems. You have to know the different architectures, you have to know the memory hierarchies, you have to know how to utilize different levels of parallelism. And now, as a domain scientist, you are at risk of being pulled away from your science and instead having to deal with this low-level details of the hardware. Now, so FleCSI addresses this by giving you a single source, a performance portable model for distributed and parallel application. So Kokkos is focused on being parallel on a single node, but FleCSI is focused on being both distributed and parallel. Okay, so it does so by supporting multiple backends for distributed, and for on-node parallelism we use Kokkos. And it provides abstraction layers that promote code reuse. Now, I won't be going into the abstraction layers of the data model and the runtime model, but the goal is simple. You want to have the scientists focus on their science and have FleCSI take care of the data migration and the execution. From a high-level point of view, a FleCSI application has this structure. You have the application, which implements the physics and the data accesses. And then that is followed by the specialization. That's the name we give it. That's the layer that translates the needs of the application to what FleCSI understands. So think of it as a domain-specific, it provides domain-specific interfaces that translate the application data to the FleCSI model. And then finally, you have FleCSI taking care of the distribution of data and managing the parallel dispatch. And so under the hood, FleCSI uses Kokkos for on-node parallelism, and it supports currently 3 different backends for distributed parallelism. So we have the MPI backend, the HBX backend, and the Legion backend. And so each of these technologies has different capabilities. So the simplest one, MPI, that just gives us explicit communication. And HBX has well-defined task execution semantics and fine-grained scheduling. And then Legion is this full-blown distributed parallel tasking system that closely matches the FleCSI model itself. Now, for the more simpler backends, FleCSI has to do a lot more work to implement the same kind of functionality as the more sophisticated backends. But the general point is that when you switch between backends, you don't have to change your application or the specialization anymore. FleCSI hides that behind its interfaces, and that gives you access to the performance capabilities of these different backends. All right, so let's look at how execution looks in a simplified way. So you have main that is executed on multiple processes, similar to MPI. And then the execution flows into the control model. Think of it as a state machine. So the high-level sequential structure of the application, which then consists of control points which launch tasks. Tasks operate on distributed data. And then we partition the data further into what we call colors. Think of it as MPI ranks, but we don't have a one-to-one mapping to cores or processes. Instead, we let the application decide what makes sense for the workload of that application. And then finally, the task can execute kernels, which then operate on a portion of the distributed data. Now with the simplified model in mind, I can show you something that looks more realistic for FleCSI, but I don't want to spend any more time on this. I only want to focus on the lowest level, the tasks launching the kernels. This is where Kokkos comes in. Okay, so this gives us fine-grained on-node parallelism both on CPUs and GPUs. The tasks always execute on the host. But so what FleCSI does, it moves the data to the correct memory space, and then the Kokkos takes care of the dispatch to the hardware threads. Now, we have this executor API, which is what gives us this consistent interface for the various execution spaces. But so we have a for all and a reduce all, which under the hood are implemented using Kokkos parallel for and parallel reduce. Now, the selection of the execution space actually happens at compile time. When you define the task, it becomes part of the, you add it to the task signature to say what execution space are my kernels going to be launched in. And so you have the choice between these four. Exec accelerator is kind of special because it is dynamic. It depends on how was your Kokkos configured. So if you have a GPU available, it selects that. Otherwise, if it falls back to OpenMP, and then finally it falls back to CPU. Since it's a compile time framework, if you specify tasks that explicitly ask for OpenMP or GPU, and your Kokkos doesn't have that support built in, you will have a compilation error. Okay, so here is just a simple example of parallel loop. So you have a task that runs on exec accelerator, so it can run on any device, GPU or OpenMP or CPU. And so in there you use the executor to do a for all. You give it an iteration space and a lambda. So it's just another layer around parallel for. Similar for reductions, you have a reduce all. You give it some accumulator function, and in this case you just sum up or you do the maximum over some distributed data. Now, calls can be changed. So we have this, you can manipulate an executor to make it more specific. Here's how you change the launch bounds, or we call it threads. So the threads and the blocks. And you can give a kernel a name, which is useful for profiling. And also here you can see the for each implementation, which is the member function implementation that gives you more control over the lambda capture itself. Okay, so the final thing I wanted to mention just on a high level, so sometimes you want to have tasks that are implemented differently on different execution spaces, so maybe you want an OpenMP implementation and a GPU implementation. We do this through C++ specialization, and so that gives FleCSI the capability to select the right implementation depending on what it figures out what it has to do. So the general gist of this is you have this struct where you define this template. This is the same as defining a task with exec accelerator, but the benefit here is you can actually delete specific implementations, like you can not have a GPU implementation and have a specific CPU or OpenMP implementation. And yeah, that's my part. So now, Hyun will talk about how you can use this to implement hard.
Okay, thanks, Richard. So I'll talk on the hard. So probably you now see that the why people are doing this multiphysics modeling, and as application scientist, I often listen that, hey, you have equations, you have a model, why do you just code it? Life is not that simple, unfortunately. Like you have multiple different components. You have hydrodynamics, radiation, how to treat the solid, how to specify the what material property through the equation state and opacities, and sometimes you need electromagnetism. If you have some special cases, you also need something called highly explosive. And then most of the cases, each system exhibit really different scale disparity, not just a physical space. Which is often people not thinking about a state variable itself. You can easily think that your density has the 10, for example, but the radiation energy is 10 to the 20. Of course, in physics, we have something called a unit, so they are not comparable. But when you actually put it into your system, that cost issue, you have 19 orders of magnitude differences when you compute something. And each component needs to treat it correctly. So when we talk on the what I mean by the multiphysics cases that also automatically involving multiscale, that is the performance challenges. You see that the some different size of your system, time scale also different, all the different physics you actually needed. So practical challenge we wanted to do, me as the people who come from the astrophysics background, how we can implement better sustainable code for developers and users with multiple background, because even we are saying we are developing the multiphysics code, our language is often pretty different. And that's the where the FleCSI will be a really perfect testbed framework. So we developed our code name is HARD, because everything is hard, but at the same time, HARD stands for the hydrodynamics and radiative diffusion. As Richard shows you, that's all the FleCSI specialization and all the different types of the backend, and we built on top of the HARD. And that's our system equation we want to solve. So you can easily think that the top 3 equations are just hydro plus some radiation energy, and you see right-hand side has all the different type of the source term we need to deal with that we need to consider. And last one also contain what we call the mass fractions, to if you have multiple materials, how you need to consider the different material among different cells. And I'm not gonna say whole details of what we have in our code, but that's the some numerical method and methodology we are putting into here. We are following a pretty standard techniques for the hydro, finite volume, HLLC1 solver, and then we have something called the multi-group. There are multiple different ways to approximate how you can treat your radiation transport. We're using something called multi-group that gives your system is mixed hyperbolic parabolic system with the steep source term. And then we also support something called the singularity EOS that can read some tabulated equation of the state and also opacity data. And we also have something called the IMAX integration scheme, implicit, explicit integration schemes to treat both hydro, radiation correctly. And also we also integrated FleXSol. You can think that that's the FleXI version of the PETSI. So we are on the same hood to use the that. And that's a pretty recent addition into our code. Since we are also targeting to the multi-material, we need to track them correctly. So we apply something called the level set method. And that combined with the extrapolation scheme, we eventually have something called the ghost fluid method. And with that, we can treat it different highly explosive materials with ghost fluid method. Point here being is that as you can see that a lot of the different numerical methods are needed to model each physics correctly. And that's where what we call the each method can wrap into the task and call into the control point to application developer adding your new physics relatively straightforward, rather than you don't need to worry about that how you can distribute your meshes among your space and just adding your physics and call it into some workflow that we showed you before. And that's the few demonstration case. First one is called the Rayleigh-Taylor instability. Why? With different type of the configuration, that's the 2D simulation, classic hydrodynamics test for it. And another thing is called the Rich-Meyer-Meshkov instability. That's the kind of same idea as the Rayleigh-Taylor, but now you hit some shocks to make this diffusive behavior too. And also we have some consideration of the radiation, how radiation affects the hydrodynamics too. Some linear studies suggest that the instability sometimes destabilize or stabilize depending on the system or opacity you choose. And that's the one type of the example we ran. Left-hand side is you can easily think that there is just hydro. And right-hand side is we now apply the radiation. So as you can see that even on the same time, radiation destabilizes this instability more. And also, in contrast, in some scenario, if you put some different type of the opacity, which also controls how radiation is hardly, and then instability is gone too. So with that, we also do some ideal some scaling test. So that's we adding all the possible physics that we want to see how it scales. We use IMAX with RK scheme and radiation in the 1D, and run some Leno cluster motion called Chikoma. And as Richard said, FleCSI also support different backends. So we also compare with just MPI plus Kokkos, and also HPX. HPX case is getting some hard time after kind of 64 node, probably due to additional load balancing we really don't encounter right now. So I think that the Flex team tried to resolve this issue. But in general, like it scales pretty well, both like MPI, MPI plus Kokkos. And then exactly same thing, but with the 3D cases. Now the size of the problem, probably hard to see that. Like we have each direction of the 2 to the 9, so you can easily that's the like 512 cube problem for the strong scaling. Same HPX, some reduced efficiency, probably due to some runtime overhead and scaling instability. But we can make it up to 1024 node. Now we are talking on the GPU efficiency. So for the radiation hydro cases, so we reach up to like 67 million cell update per second, which is kind of 7 times acceleration over like a 128 cores Chikoma just CPU node. And then we ran onto the NVIDIA A100 GPU Chikoma cluster with MPI backend. And we do some, maybe some people claim that this is an unfair comparison, but we also try to find that how we can compare with the open source, another radiation hydro called the Quokka. It reaches up to like about 40 million cell update per second using GPU. Our case is about twice faster than that. Then now with that, we ran the Capitan Alamos radiation case in 3D. So with the different with the different numbers of the GPU on Chikoma, same architecture, it can about run up to like 2 to the 7, so about 128 GPU nodes shows pretty nice efficiency. So we then compare with that the CPU versus GPU weak scaling, so CPU top row. So this is perfect speed up for the strong scaling, and also about 50% efficiency on the like 8192 rank. And GPU is good speed up to 32 length, and it's about 80% efficiency, about 128 GPUs. So we are currently looking like why this happens, and also how we can improve it better, especially with some realistic physical simulation cases. So with that, so that's the conclusion. I hope that the modeling multiphysics system is essential, but very challenging. I hope that I convinced you. And that's the reason that the FleXi and FleXi specialization that provide a really perfect path for the code design. And we demonstrated different type of the problem using the code hard, and the currently hard is evolving. It is starting with the group of the students during the summer school at Lano called the Code Design Summer School 2024. So within 2 years, we are very happy that we have adding a lot of different physics, run on the multiple GPUs, and then providing some like production data for the different area of the application at the Lano. But we are adding much more physics and also tackling on the different type of the architectures to scales better. And FleXi and hard both are open source. So if you're interested in using how to hard itself, you can go to our GitHub, clone it, run some tests. And also if you want interested in using how to using FleXi to develop your application code, also it has a really nice documentation to build the code. So I encourage you to check both. So that's it, thanks. Any questions?
Why did you make the member function, static member function templates, well, a template instead of just an overload? Was that simply so you could define them outside of the class?
Yeah, there's a limitation in the language that we can't do it outside. You can't do the template outside.
I kind of hate it, but I understand.
Yeah, that's exactly, that reaction is normal.
Hey, it's a very cool talk, thank you. So I was kind of wondering, since you're trying to like interface with application scientists and sort of make it easier for them to work with these very parallel systems, I was thinking, is there any like, are you worried about mission creep on certain like applications that would be beyond the area? Have you talked about that? Like, for example, would this be, like, would it be interesting to your team to look at like soft matter physics, for example, using this? Or
I mean, so the application built on top of the FleCSI were originated. Some people demand us to do, and I mean, we didn't mention specifically. So we have a different kind of so this one target for the high energy density physics. We have a lower energy density physics called the MOIA. They are working on it, not open source, which is Lano internal, but as far as I know, that also works pretty well. So I don't see any intrinsic barrier if you want to adding new physics on top of this system. Maybe someone disagree, but yes, I think they should work. Any comments?
No, it's FleCSI is trying to be generic. It's trying to solve the hard generic problem, and so then you have different codes like hard and MOIA they're implementing the different types of simulations you want. We have something that is, we have abstractions for particulate systems, we have abstraction for meshes, and so, yeah, we haven't had so many outside users from Lionel, but we're hoping to get some.
All right, any other question? All right, thank you guys very much.
Thanks.